Alright, so we're looking here at the second section of chapter 3, and this is going to be a short section. It's not really all that complicated, and there's not actually a lot of work to it. But we're going to talk about differentiability. And differentiability, and we'll mention this and define it 2 or 3 times the same way. Differentiability is just the ability to take a derivative. If a function is differentiable, that means you can take the derivative. Now, typically we're going to talk about differentiability at a point and whether it is differentiable at a point or not. And because while it is good to know about the entire function, more specifically we're going to look at specific intervals and even specific points. All right, now to be differentiable, a function must be continuous and smooth. Derivatives will fail to exist at corners, absolute value of x, it's not differentiable at 0. Everywhere else now this thing is differentiable. At x equals 0, the absolute value of x is not differentiable because of the corner. Cusp is another place that it's not differentiable. This is a function of f of x equals the x to the 2/3 power or the cube root of x squared, and you get this pointy thing here. And what we're looking at is the slope here is negative, 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 then all of a sudden, boom, it's positive. It doesn't gradually transition into the next slope and the next slope and this next slope. We've got a place right here at 0. Once again, it's not differentiable at 0. It's differentiable everywhere else. But at 0, we have that sharp transition, that sharp change of slope from a negative number to a positive number with no nice transition through. All right, we can also be non-differentiable when we have a vertical tangent. Once again, at x equals 0 here, our tangent line goes vertical. Well, differentiability means that we can put a number with the slope of the tangent line. We can actually put a number with the slope of the tangent. In this case, with that slope being undefined or being vertical, we know we're going to rise a lot and we're not going to run at all, so we got division by 0 error for our slope at this point right here. So that's why we cannot define that with a number. All right, and then of course we've got the easy one. The easy one is with a discontinuity. Remember, a function must be continuous to be differentiable. If it's not continuous, then it cannot be differentiable. So that's one of the first things you look at. If you're looking for places where a derivative is going to fail to exist, you look for a discontinuity. All right, now most of the functions we're going to study in calculus will be differentiable. All right, now let's look at 2 theorems here. The first one says if f has a derivative at x equals a, then f is continuous at x equals a. Now we're going to boil this down just a little bit more, and a little statement that you need to remember is this: differentiability, forgot my I there, implies continuity. Now, that's a fancy way and a short way of saying if it's differentiable, we know it's continuous. So if you are told or you know that you can take the derivative of something, of some function at a point, then you know it has to be continuous at that point. Now, you need to make sure that you understand this is not one of those if and only if things. If you have this situation here, if you know differentiability, you know continuity. If you know continuity, that does not mean that you know differentiability. Think about the absolute value and the cusp and the vertical tangent. Those are all they're all continuous at the point where they're not differentiable. So just because it's continuous does not always mean that it's differentiable. But if it's differentiable, it guarantees that it's continuous. And there's the reason why. Since a function must be continuous to have a derivative, if it has a derivative, then it has to be continuous. But just because it's continuous does not mean it has a derivative, so be careful. Now, the second theorem we're going to talk about, I'll be honest, you're not going to use very much, but it is good to know. It says, if A and B are any 2 points in an interval on which f is differentiable, then f prime takes on every value between f prime of A and f prime of B. Now, this is the intermediate value theorem specifically for derivatives, but it's very similar to the intermediate value theorem we are used to already. So if we know that our function is differentiable and A and B are 2 points in an interval, in that interval where it is differentiable, then the slope at one end and the slope at the other end are going to sandwich what all the slopes inside are. What that means is this. If I've got this graph right here, this little function, and I find over here at A, my slope is 1/2, and I find over here at B, my slope is 3, from A to B, I'm going to take on every value between f prime of A and f prime of B. Now, it doesn't mean that I don't take on values outside of that, just like the intermediate value theorem before, but I'm guaranteed that I have a point in here, somewhere in this interval, that I'm going to have every value that's greater than 1/2 and less than 3. It doesn't have to be this simple. It could go up and down and all kinds of craziness like that, but it's still going to have every value between 1/2 and 3. It'll have some extra values in there also, but it will have every value between 1/2 and 3. Once again, this is one of those existence theorems where it tells you that it exists, and then it says, well, okay, you can go find it, or find where that happens. So in this example here, between A and B, f prime must take on every value between 1/2 and 3. No matter what value you can come up with between 1/2 and 3, there is a point somewhere in here that we could find if we knew the function. You know, we're talking 2, we're talking 1.78934, we're talking any value at all between 1/2 and 3. All right, see, told you, short to the point, no big deal.